Hello, everybody. Welcome back. So this is the second part of our very first lecture. And in this part here, I would like to introduce you to some really fundamental concepts of cryptography. So the topics that we're going to cover today is absolute security with the one-time pad, permutations and modes of operations, which are two abstractions that we use very often, principles of modern ciphers, measuring security in bits, and then I would like to give you an overview of attacks on cryptographic systems. As I told you in the last lecture, cryptanalysis is not something that we concentrate on here in the class, but occasionally we are still going to talk about certain attacks in order to understand why we adapt our cryptographic algorithms the way we do. Okay, so let's start with the first topic, absolute security. So the question is, can we ever achieve absolute security, 100% security with a cipher? So it turns out we can actually do that. And the cipher that is achieving that is called the one-time pad. So this cipher is virtually unbreakable. And unbreakable means with unlimited resources. Unlimited computing resources to begin with, and unlimited time. So the one-time pad works like this. This here is the encryption side. So this is the E part of the cipher. This is the D part of the cipher. So we have sorry about that. So we have our plain text, and the plain text is encrypted into the ciphertext by way of a key. So, and on the decryption side, we have our ciphertext, and this is going to be decrypted into our plain text, again, using the very same key. So the question is, how does the encryption and decryption work? It's actually very, very simple. What we do is the algorithm that is being used is the XOR operation. So I assume and don't want to talk much about it, about the XOR operation, because you are all computer science students and should know about it. So very, very roughly, if you have the XOR operation and you XOR two values, so 0, 1, 0, 1, 0, 0, 1, 1. So let's assume that we want to connect, these two pairs of bits with an XOR operation. What would the result be? Well, the result, it turns out, is a 1 wherever the two bits are different, and it's a 0 where they are the same. So this is one way of looking at it, to say that we get a 1 if the two bits are different, and we get a 0 if the two bits are the same. So this is one way of looking at it. Another way of looking at it is to consider this bit here, this one here, as a question negate. So the question negate is applied to the bits on the left-hand side. So when you look at the XOR operation that way, we ask, do we want to negate that 0? No, so we get a 0. Do we want to negate this one here? No, we get a 1. So do we want to negate this 0 here? Yes. So we get a 1, we negate the 0, and the same thing is true here. Do we want to negate this 1? Yes. So we get a 0, which is the negated 1. So this is just a quick explanation how the XOR works. It's a really cool operation, especially also because it doesn't have any carryovers. So you see that the cipher is extremely simple. It consists of that one operation, the XOR. But here comes the thing. The length of the key, and this is very, very important and is the underlying reason why we have absolute security. The length of the key is exactly the length of the plain text. So if you have 5 gigabytes of data to encrypt, like that Hollywood movie that you downloaded illegally, you need a key of 5 gigabytes. Okay, so this is one requirement. And the third and last requirement is that we have absolute randomness in the key. So the key is absolutely random. You may derive that randomness from, natural processes, thermal processes, physical processes, or random number generators generated in a computer. But the requirement is that the bits in the key are absolutely random. There's no pattern in the bits in the key. Okay, so the algorithm is actually totally symmetric. So when we say that symmetric, what we mean by that is that the part of the cipher that is encryption is the very same part as the decryption. So which means that we apply the very, very same operation. And the question is, why does it work? So it works because we basically XOR the key. First off, we XOR the plain text with the key, and then we have the ciphertext, and then we apply the key again in an XOR operation on the ciphertext, and we get X back. And the reason why that is if you listen carefully, we actually apply the XOR with the key twice. So we basically XOR the key with itself. And what that means is that this always evaluates to 0, whatever the situation is. Okay, so if you apply, if the key bit is 1, and you apply an XOR to that very same bit, what you get is 0 here. And the same is true if the key bit is 0. 0 XOR 0 is also 0. So in other words, if we apply the XOR operation twice, it doesn't change the original plain text. We retrieve the original plain text again. So now the question is, why is this one-time pad cipher unbreakable? There's, you can mathematically prove that, and actually Shannon, the information theorist, the famous theorist of information sciences, he actually did that. He provided a theoretical proof that this is absolutely unbreakable. But I would like to go on a slightly more popular, easy to understand approach, why the one-time pad is actually absolutely unbreakable. So just consider that we have an input that is all zeros. So whatever that would make sense, is a different question, but let's just assume that the input is all zeros. What would you see on the receiving side? what you would see is a random bunch of bits, which is the key. And you cannot infer from these random bits that the original input was all 0. So no inference can be made concerning the input if you look at this bunch of random bits. Another rationale is, again, intuitively speaking, is if you have, as an attacker, you have retrieved the ciphertext, basically because you do not know the key and the bits in the key are totally random, you have to assume any key. So any key could have been used to receive the ciphertext. So assuming that any key created that ciphertext, you can basically construct out of that ciphertext any arbitrary input, any arbitrary plain text, depending on what key you assume. And the key space is huge. It's the length of the plain text itself. So it's really impossible to draw any conclusions if you have given the ciphertext what the plain text is if you do not have the key. So two things are critical here. First off, the key, and I don't mention that again, the key needs to be as long as the ciphertext, the plain text. And the other thing is that the key needs to be truly random. And from an operational perspective, you can use the key only once. This condition is the reason why this cipher is called the one-time pad, okay? You can only use the key once. And you may have heard about, in history, what happens if the key, breaking this protocol and assuming, okay, damn it, it's such a pain to generate a random key all the time. So you may run out of random keys and you decide to, not take it as seriously and actually reuse a key. Well, there's historical evidence that in the US history, after 1945, there were the Rosenbergs spying on the US and leaking top secret information to the Russians. And they were caught and executed afterwards. And the reason was that the key that they used was used several times. So why is it so dangerous to reuse a key? So let's assume, I should have, let me replace that. So if you know that a certain ciphertext got encrypted with a certain key, and then you have a second ciphertext that got encrypted with the same key, what you can do then is, so we are here, okay? The same key applied to two different plain texts, and we retrieve two ciphertexts as a result. So an attacker can actually do the following computation. The attacker can do Y1, XOR the two ciphertexts. And what does that mean? It means that basically the key cancels out. So this key cancels out for the very same reason why the one-time pad works to begin with. Remember that a key XORed with the key is actually 0. So that doesn't mean that we get the plain text right away. What that means is, however, that we get the XOR of the two plain texts. So now it's getting interesting, because if you do know, by any chance, if you do know pieces of one of the plain texts, you can compute the other plain text. So, and there are always, opportunities to actually, at different levels of attacks, to know about parts of the plain text or the whole plain text of, one of the two plain texts. So one option is that, like in file formats, there is some initial fluff information that always looks the same, configuration information in a file, or just file content following a certain format, and so forth, that you may know parts of the plain text. Another very likely situation is that you may have the sender actually encrypt a text that you know, and the sender is unaware of that he or she did that. So there are attacks where it's you may think of a situation where you just smuggle in some text and it gets encrypted by the sender, and that way one plain text and make inference as to the other. So again, this is different levels of attacks and different levels of involvement of Oscar in the triangle, Alice, Bob, and Oscar, when Alice communicates with Bob, okay? So there are very practical things that you can do to make that happen. So anyways, what we understand now is that if parts of X1 are known, parts of X2 can be constructed, and vice versa. So this is very dangerous. And that's the reason why you strictly have to use the key, a key only once. So why don't we just use this one-time pad all the time? Because it's absolutely unbreakable. Well, the thing is that it's impractical. And the reason why is, and the sole reason actually, is that the key is as long as the plain text. So basically you double the data volume. And the other danger is that you may reuse a key, which is not a good idea either, as you know already now. So that's the reason why the ciphertext, the one-time pad is not practical, but it actually defines a milestone. So this leads us to the next, so let me see. Yeah, we're going to talk about this a little bit later down when we talk about principles of modern ciphers, absolute versus relative security. So what the one-time pad is actually doing, it defines a desirable outcome on the far extreme on one side versus the far extreme on the other side, where ciphers are incredibly insecure, like what we have seen happens with the historical ciphers. So obviously that defines a space, and modern cryptography lies somewhere in between, pretty much having no security versus absolute security with the one-time pad. And that said, that's the reason why the one-time pad is so interesting, because we need to define our own space in between those two extremes. Okay, so let me talk about the next, switch over to the next topic, which is permutations and modes of operation. So from what you have seen so far, basically ciphers at two extremes, we can abstract out two concepts that are important for our modern cryptography. The first one is we need to have a permutation. A permutation is a function that transforms one item into another item, and that transformation has to have a unique inverse. So you have seen, the simple permutations in the Caesar cipher, where letters are mapped in a fixed way. So in modern ciphers, that permutation is actually changing depending on a key. So the permutation is determined by a key. So, and it's important that different keys, they result in different permutations. Of course, I mean, we understand that, but we need to lay down these principles. And permutations need to at least look random, but ideally they should be random, okay? But they need to look random enough that an attacker cannot see any scheme, any repetitions, any structure in the ciphertext. So it's important that different keys, result in different permutations. The randomness is important, and the unique inverse is important. So we need to be able to decrypt a ciphertext back into the plain text, and if the inverse would not be unique, we may receive different plain text for one ciphertext, and of course this is absolutely useless for our purposes. So the other abstraction is what we call mode of operation. Mode of operation. The mode of operation is an algorithm that uses permutations to process messages of any size. So an example that we are going to cover, permutations versus mode of operation, the most popular example is actually to look at AES, which is the Advanced Encryption Standard. And the Advanced Encryption Standard just by itself provides for an incredibly secure permutation. But it turns out that it's not secure enough if you encrypt large texts block by block. So it's a block cipher, block by block. Just like that, just purely, applying the AES algorithm to blocks of code. What you need to have is a mode of operation so that the same block of information does not translate into the same ciphertext. And this is being achieved by the mode of operation. And we are going to talk about that when we talk about block ciphers. So let me give you a few examples. So when we look at Caesar and Vigenère, both use simple substitutions, okay? This is what the permutation is. And the mode of operation for Caesar is really primitive. Caesar uses the same permutation on all letters. So in other words, the mode of operation for Caesar is very primitive as well. And we know that, but we just want to make, the case. While Vigenère is more sophisticated, it uses different permutations per letter. And remember what I said is that the same letter may result in different, or almost certainly will result in different letters depending on the letter of the key that is being used to encrypt a certain letter. So the same letter E throughout the text will be decrypted differently anytime when you try to encrypt it by way of the Vigenère cipher. So this is a matter of mode of operation, you know, how the permutations are applied in reality, in practice, to encrypt and decrypt information, so large texts. Okay, so this concerns the mode of operation, and Vigenère is more sophisticated in that. Okay, so one quick question to check on your understanding: can you make Vigenère absolute secure? Well, anybody? Oh, yeah, you can't answer. So it turns out that if you make the key as long as the plain text in Vigenère, and the key are totally random bits, Vigenère is actually morphing into the one-time pad, and as such, it would be absolute secure. So it should be easy for you to convince yourself if you apply Vigenère that way, with a key as long as the plain text and the bits are totally random, then we essentially have transformed the Vigenère cipher into a one-time pad cipher. Okay, so next topic, and I touched on that already, principles of modern ciphers. So here I want to talk about some really fundamental ideas about modern ciphers, which I distilled out and normally are not being named explicitly as I do it here. So this is kind of a novelty, and yeah, consider yourself to be happy to be in that class. So the first idea is absolute versus relative security. What you saw is the one-time pad provides for absolute security. Absolute security. So what does it mean? It means that the cipher is absolutely unbreakable given any amount of time, any amount of computing resources. So this is important because this touches on the practicality of actually attacking certain ciphers. In reality, we do not have unlimited time and we do not have unlimited computing resources. And it turns out this is what exactly modern ciphers are counting on. So again, on the one side, we have absolute security. On the other side, we have, you know, historically speaking, we have inherently insecure ciphers, and again, typical ciphers are classic ciphers. So the reason why they are inherently insecure is the secret may lie in the cipher itself. So like, you know, the Caesars or my grandmother's cipher, or the key may be too short. We just saw that with Vigenère. If we, however, make Vigenère, the Vigenère key as long as the plain text, we actually have an absolute cipher, but in reality we don't. And other principles that these ciphers don't implement, and we're going to talk about in a second. It has to do with confusion and diffusion, and this is what historical ciphers also do not do, and that way a ciphertext would allow for conclusions made back as to the plain text. So, as I already said, we see some, you know, two extremes: absolute security on one end, inherent insecurity on the other hand. And what modern ciphers seek to do is to get some middle ground. Okay. So this is important. And what we achieve here is we achieve relatively secure ciphers. So what does it mean? It means relative security means that the key length is small enough, but it's still practical to use it. And it's still impractical to break because it takes too long and it takes too many resources. And this is important. Modern ciphers actually rely on the impracticability to break the cipher, which means, if you look the other direction, that if you have unlimited time and unlimited computing resources, we have to say that modern ciphers are breakable. They are breakable. They are not absolutely secure. They are only relatively secure. So given unlimited time and computing resources, modern ciphers are breakable. But this assumption that we have unlimited time and computing resources is not realistic. Okay, so that's very important and interesting at the same time. So in summary, so security, we can have absolute security, we can have relative security. So which means that absolute security we call informational security. Informational security, that's the word here, which means that they are theoretically unbreakable. They are not breakable under any circumstances. So versus relative security, which is actually computational security. So it means that those ciphers are practically impossible to break. And they are practically impossible to break because in reality, in practice, we do not have unlimited time and unlimited computing resources. So that's the bet that we make. We rely on relative security because of the impracticability of having unlimited time and unlimited resources. Okay, so another idea is confusion and diffusion. So we talked about permutations and modes of operation. So an important principle is to exercise confusion and diffusion. And we will see that applied diligently in the AES algorithm, which is the most modern, the most advanced block cipher to date that is at this time deemed to be absolutely unbreakable. I mean, I shouldn't say absolutely. We know it's relative security, but in practical terms, it's not possible to break AES. So it relies on these two principles, confusion and diffusion, and I will tell you what that means. So let's start with confusion. So what you want to do with confusion is to make the relationship between the plain text and the ciphertext as complex as possible. So you want to make absolutely sure that there is no way to make inferences given the ciphertext back to the plain text. So this is one principle. And you will see that in the AES, there is something called the substitution box. And the substitution box in AES is actually achieving that. It achieves confusion. So you create confusion on the attacker side because the attacker is totally confused and cannot make any inferences from Y back to X, from the ciphertext back to the plain text. So diffusion is a bit different. So what you do in diffusion is to spread the seeming randomness across all over the ciphertext. So you rearrange the bits in a message such that any redundancy in X is spread over out over Y. So any change in the input in the plain text, the changes are spread all over the ciphertext. So the result of that is, and this is important here, and it's in principle hardly ever named anywhere, but that's what it comes down to, that with modern ciphers, in accordance to what we just talked about, confusion and diffusion, modern ciphers change like on the order of 50% and above bits in the ciphertext if just one bit changes in the plain text. So just imagine that you change a bit, a single bit in the plain text, which results in a change of at least 50% of the bits all over the message in the ciphertext. So, and this is interesting, and this is a fundamental, basically rubric to check modern ciphers against. Okay, modern ciphers should comply to this rule, and they do, of course. Okay, so how do we measure security? How can we say that security is such and such and such? So what we mean by security is actually computational security, and we need a computational security measure. And the best shot that we can get is somehow measure security as a number of bits. That would be an easy, to handle metric, if you want, to measure security. So it turns out we actually can do that more or less. So a cipher is T-secure. We say T-secure if an attack needs at least T operations. So in order to break a cipher, we need to have a number of operations. And that number of operations can be taken as a measure for the security of that cipher. And what we can do is we can express that number in terms of bits. So, and that gives us an n-bit security, okay? So if we have a number T, we can translate that number into the number of bits to represent T. So in other words, what we have here is we compute n up here such that T is 2 to the power of n. So it should go without saying that n is actually the number of bits of T. So in other words, we compute n as LGT, and in algorithms actually, and here for our purposes, LG means a logarithm base 2. So logarithm base 2 of T is n, and n is the number of bits, and that's what we say we have that many bit security. So it turns out that, this is underlying that idea is actually a brute force approach. So if we have a key that is n-bit long, what we actually get is not automatically n-bit security. It's at most an upper bound, actually. So n-bit key provides at most n-bit security. So the question is, why is that? So if we have a key, for instance, of 1024 bits, that does not necessarily provide for 1024 bit security. And why is that? So why is that an upper bound, but in reality, the security may be smaller? Well, the reason for that is we may know about attacks that do not need to take a brute force algorithm, a brute force approach, but can break the cipher by way of different methods, different approaches, other than brute force, in way less steps. So upper bound, likely smaller in reality. So keep that in mind. The cipher may be broken in fewer operations than expected, and this has to do mostly with not trying all keys. We do not need, for some reason, try to all keys, or there may be a method, known or unknown. I shouldn't actually say unknown because that would be dangerous. There's a method, known or unknown, for factorization, for instance, which is a hard mathematical problem that ciphers rely on. Or we may choose to just use a way different and higher number, bit number key, because we know of attacks that achieve, breaking the cipher in way less steps. So we will see when we talk about ciphers that, for instance, some attacks allow for a square root of the number of bits to break a cipher. So let's say we have a key that uses 1024 bits. And well, we find out that somebody published an attack that actually needs the square root of the number of operations, of the key length. So in other words, instead of 2 to the 1024, 2 to the 512 operations need to be done. So way less operations need to be done in order to break the cipher. So let's write that down as an example. So we have, 2 to the 24. If we have an attack that not using brute force, but uses just the square root, of the number of keys, we have essentially a security of 512. So in order to get that security up to 1024, if this is what we're shooting for, what we need to have, we need to double the number of bits in the key. So in order to achieve a 1024 security level, we need to have a key length which is 2048. So we basically, in order to make up for that halving of the key length, we double the key length again, which means that with a key length of 2000 bits, we have, because of the nature of attack, essentially a security level of 1000 bit. So in other words, you see that the discussion on the key length is a feasible one when we want to define security in terms of bits, but it may not tell the whole story. So if we have an RSA key, for instance, which is 2000 bits long, we essentially only have a security level of 100 bits, okay? So because of the nature of attacks that are available. So you have to distinguish between the security level, what it seems to be, versus the practical security level that we actually have because of certain attacks that eat away on the key length, okay? All right, so here's a link that allows you, that would allow you for looking up, different key lengths for certain ciphers that are considered to, to be secure these days. Okay, here comes our last topic for this second part of lecture 1, which is attacks on cryptographic systems. So in other words, we speak about cryptanalysis. So cryptanalysis, how to break ciphers, has different parts. So cryptanalysis has different branches. And classically, we want to break a cipher by really looking at a ciphertext and either try all keys. Normally, that would be called brute force, or we have analytical methods that allow us to get to our desired result way faster compared to brute force. So there are a lot of, different attack models out there that act on modern ciphers. And again, this touches on the fact that we actually, we publish our ciphers, and that way we have an idea and get feedback what methods exist out there that are capable of breaking our ciphers, and we can adapt accordingly, and that keeps our ciphers secure all the time. And there are two ways of reacting to, a new analytical method that some researcher usually comes out how to react to that. One example I gave you above, if an attack becomes known that only needs a square root of operations, from the original security level, we can, we can increase the key length, or we can desert and relinquish and basically junk a cipher altogether and replace it with a more modern cipher. So this has happened with a cipher that was very well known. It was actually a really good cipher. And the name of that cipher is DES. DES has been the standard for quite some time. Its problem, however, was that the key length was too short. So there was an updated version of DES, which is triple DES, which was a remedy on the key length, and the key length was increased. But eventually it was deemed to be computationally too expensive, and DES was replaced altogether by AES, which is the advanced encryption standard, which is the current standard that we're using right now. And it seems like there's no attack out there that we think could materialize in the near to far future that would be able to break this cipher. So one looming threat on the horizon is actually, if we actually have practical quantum computers, that would question quite a few ciphers, and researchers already now are working on new ciphers that are immune and robust against quantum computer attacks. What is interesting here is that we actually do not know whether quantum computers will ever materialize because of the technical difficulties. But researchers are already working on models, what the world would look like, what the cryptography world would look like if such machines would exist. And they already have, algorithms in place that are robust against these attacks with quantum computers. So it's very interesting. And this is a topic, by the way, that we are going to cover in the next class, the second class in the sequence of these two classes of cryptography. Again, this one is about the foundations and the next one is about applications. And one of the topics we are going to cover is what the world will look like if we have quantum computers. All right, so apart from that, and which is actually not any of our concerns, has to do with social engineering. Social engineering seems to be a low-cost way of stealing, plain text by luring people into, whatever social engineering is doing. I don't want to get into the details, but it's basically a way how to avoid actually apply analytical methods because our modern ciphers are just too robust to be cracked easily, and social engineering would be one way to just avoid the whole area of trying to crack a cipher at an analytical level. So, and the last one that I also do not want to comment a lot about is implementation attacks or side channel attacks. Side channel attacks. What does it mean? It means that you do not really look into how a cipher works mathematically. What you do is you use other kinds of information like power consumption, radiation, and things like that. So you make measures on the implementation. So how is a certain mathematical cipher implemented practically, like at the electronic level? And you make, as an attacker, you take measurements, all kinds of different measurements, and maybe even temperature, power consumptions I mentioned, and so forth, in order to draw conclusions from the ciphertext back to the plain text. So none of this here, social engineering implementation attacks, is of our concern. So when we talk about attacks at all, we talk about analytical methods that would be able to, break ciphers, and what our response to that is. Normally, brute force is not considered either. Modern ciphers are way too robust against brute force. Brute force would imply such a huge computational cost that all the computers in the world, would not be able to break a cipher during the lifetime of the universe. So brute force normally is not an option. Brute force is only used as a way to juxtapose against analytical methods and have an understanding of how much better a certain attack is compared to brute force. Okay. So let's look at the very, very few, and this is not representative of what's out there. Let's look at a few examples, like Caesar's, Caesar cipher is very, very weak. If you widen it up and say, okay, any kind of shift, you know, instead of just always shifting by 3 letters, our key basically is kind of like the number of shifts that we apply to the plain text in order to translate it into the ciphertext. So convince yourself that the key space is really small. It's actually 26 because we have only, or let's say 25 because you don't want to shift by 0 positions, then you have the plain text anyways. So and letter frequency analysis, you know, may be a good way of finding out how many shifts were actually applied. So here's a link that I gave you, I'm giving you because this link, the information that you find behind that link, comments on the frequency of letters in the, you know, English alphabet in the English literature. So yeah, I don't want to go into Morse code and Huffman code. Huffman code is a way of compressing information, and the idea is that you give higher frequency letters shorter codes. So the idea is, or the goal of the Huffman code is, and we are going to talk about it in algorithms in 421, the goal is to actually shorten information, to compress information. You know, think zip, for instance, is doing that. So, and again, the idea is higher frequency letters get shorter codes, and that way you shorten the overall information, and just your information takes up less space. So Morse code, you know, I have been a radio officer in the East German Marine, and I had, back then, we actually still used Morse code. And, you know, I had a Morse key, and I was transmitting information from all over the world back to East Germany using that technology at the time. And Morse code also, when you look at the way how letters are encoded by way of dots and dashes, you know, a short versus a long signal, you will also see that the Morse code actually honors the principle of giving, you know, higher frequency letters in the English language a shorter code. That's the reason why, you know, we have the I is just 2 dots, the T is 1 dash, the E is 1 dot, and so forth. So these high frequency letters, they have a short code. Okay, so let's get to Wegener. Brute force seems to be infeasible. It depends on the key lengths, of course, but yeah, it really depends on the key lengths. So the longer the key, the more infeasible brute force becomes. And letter frequency analysis is not applicable, or at least very, very hard to do, because the same letter is potentially being encrypted with different ciphertext letters. So that makes frequency analysis really hard. You can get certain clues if you know how long the key is. Then a more complicated version of the frequency analysis may be feasible, but in reality, it's hard to do. So those are historical ciphers. This is in total contrast to modern ciphers. The security of modern ciphers, I said, relies on the impracticability we do not have unlimited resources. We specifically do not have unlimited computational time and computational resources. And that's what modern ciphers rely on. So what is it that takes so much resources, so many resources? It's actually normally a hard to solve mathematical problem, which is really hard to reverse. So we speak about one-way functions, and once you encrypted something, which is easy to do, the way back to the plain text is very hard to do. And the funny thing is that these mathematical problems are well known, but they're just hard to do. And there are, for many of them, or for all of them, no good ways to solve that mathematical problem in a reasonable time. So that right now, as we speak, the two basic mathematical problem that our today's ciphers security relies on is prime factorization. So what does it mean? It means that if we have two prime numbers, two large prime numbers, I have to say, and you factor them, and you get a result of an even larger number, of course, then it's really, really hard knowing the number, the result. It's absolutely hard to actually find the two original prime numbers that were, the original factors of that result. So this idea is being used in RSA. The problem with RSA is it's still being used, but it's computationally very, very, very intense, very intense. So that is one thing. And the other thing is the computational distance, so to speak, to actually assault and try to solve the prime number factorization versus do the computation in RSA, that computational distance has become smaller over the years. And I would think that at some point in time, RSA is not worth using anymore. But that's not a problem because we have another hard to solve mathematical problem, which is the discrete logarithm problem. And we are going to talk about it at length. The discrete logarithm problem, or DLP, is the underlying idea of the Diffie-Hellman key exchange. It's the underlying idea of a number of asymmetric public key cryptography. So by the way, these are all public key cryptography systems. So the discrete logarithm problem is also underlying the elliptic curve cryptography cryptosystems, which you may have heard, which is the latest incarnation and the most popular, becoming the most popular public key cryptography systems. So systems that rely on the discrete logarithm problem. So I'm giving you 3 links here, and I would invite you to just have a look at those. And it touches on the prime factorization problem. It turns out that over the years, RSA is, a very popular, as I said, very popular public key cryptography system. It was invented by 3 guys from MIT. And it's also the name of the company. And that company, RSA, over the years has given out challenges out to the world for anybody to solve, just to get a feeling as to what key length is actually, sufficient in order for keeping RSA secure. And it turns out that those factoring challenges, that researchers are already at a key length of 700 something, and you can read it up. And they could break keys with that length in reasonable time. So that's the reason why RSA, uses keys that are way longer than that, just to keep the computational distance and keep RSA secure. All right, so I hope you learned a lot during this lecture. So we touched on a number of very foundational principles of modern cryptography, and I hope you enjoyed it. And those are so fundamental that they basically reappear over and over and over again throughout the class for the rest of the semester, without ever possibly being mentioned again, or only occasionally mentioned again, but always keep them in mind, okay? Okay, thanks for listening, and I see you in the next lecture.